We've had some coffee here in Leiden. I will actually take the opportunity very briefly to turn around the laptop so that you can see who is here. So you can all wave at our online audience here. So we have a nice large room here. And as we are getting started. So our first speaker now is Aymeric Brand. I will add him to the stream here. Yeah, he's already all set. That's great. So hi, Aymeric. He will talk about what are the best observational tracers of the ionization fraction in the ISM. So Aymeric, take it away.
Thank you. So hello, everyone. So yeah, I'm going to talk about how to measure the ionization fraction from observations. So as you all know, the ionization fraction is the fractional abundance of free electrons in the gas. And here I'm going to focus on the neutral and molecular part of the ISM located in giant molecular clouds. So the ionization fraction is a key parameter of the gas in the ISM for several reasons. First, it allows the development of chemical complexity because ion-neutral reactions are usually much faster than neutral-neutral reactions. It also controls the coupling of the gas, the dynamical coupling of the gas to the magnetic field, especially, for instance, during the collapse of prestellar cores. And it also affects our interpretation of key molecular tracers because electrons are very efficient collision partners for high dipole molecules, dipole moment molecules such as HCl. So in the ISM, there are two main sources. If we leave apart shocks, there are two main sources of ionization. In regions that are not too much shielded from the UV photons coming from the stars, the main ionization process will come from stellar UV photons. So very close to the stars, everything is ionized and the ionization fraction is close to 1. Then we move to regions where the only UV photons left cannot ionize hydrogen, but they can ionize carbon, and then we'll have an ionization fraction closer to 10 to the minus 4. Then it will decrease up to some point where stellar UV photons will become negligible, and it's cosmic rays that will dominate the ionization. And then the ionization fraction is usually found between 10 to the minus 6 to 10 to the minus 9. So now the question is, how can we measure this ionization fraction? The difficulty is that usually we can't observe directly the main charge carrier in the gas. So we use indirect tracers, which are molecular tracers that are sensitive to the abundance of electrons through their chemistry. So what has been most commonly done is using deuteration tracers, such as the ratio of DCO plus over HCO plus, based on a fairly simple idea, which is that DCO plus over HCO plus traces the deuteration fraction of H3 plus, and that this deuteration fraction, as you know, it's H3 plus, H2D plus is enriched at low temperature, but this enrichment is limited by electronic recombination. And so this DCO plus over HCO plus ratio should be sensitive to the abundance of electrons. You see here a simple analytical approximation based on this simplified network. Of course, it's dependent on the deuteration fraction because the first step, the link between DCO plus over HCO plus and H2D plus depends on the gas phase abundance of carbon. But there are more limitations. If we look here at the result of full chemical network, chemical models with full chemical network, we see that the results are a bit different. Of course, the simplified analytical approximation is still an approximation. But more interestingly, we see that there is a large scatter in the relationship, and it doesn't all come from the depletion factor, but a lot of it comes from the ortho to power ratio of H2, because the enrichment of H2D plus is very dependent on this ortho to power ratio. So that means that if we want to use these tracers, there are several other physical parameters that are not directly observable either that we need to know to have a precise relationship. And the last problem with this tracer is that deuterated molecules are faint, so usually they are only observed in a very small fraction, in a very small spatial extent of the cloud. And here our motivation to try to go further was the Orion B large program at IRAM 30 meter. So this program we tried to cover the whole giant molecular cloud, so a field of 5 square degrees. We see here only the first square degree at a resolution of 26 arcseconds, so with a large range of dynamical scale, and covering the whole band around 100 gigahertz. So the idea here is to have an unbiased dataset that's not focused only on a few bright regions where people used to do spectral surveys, and that's also not limited to one single line over a full map, but that has both the spectral information and the spatial information in order to tackle, from a statistical point of view, the big questions about GMCs and star formation. So here we see that if we want to try to estimate the ionization fraction in this dataset, we'll need something more than DCO+, because DCO+ is only detected in a very small number of pixels over this map. So the usual approach to try to determine some unobservable parameter from chemical models is that we have some observations of some lines, we compare ranges that fit the observations, and we try to reconstruct a map of the physical parameters. The problem is that if the lines that we have are not sufficient to constrain the parameters, we can't get any information. So here we try to use this noise. We can build a grid of model where we sample randomly across those unobservable parameters with a minimum a priori information, so just a uniform distribution with some mean and max values. And then what we need is just some chemical model to build a model grid and some way to estimate for each potential observable tracers its predictive power to predict the ionization fraction. So first, the model grids, we use stationary chemical models with a full chemical networks with 310 species. We explored a large number of physical parameters. So here, because we expect that the best tracers might not be the same in different types of conditions, we actually built 2 different model grids, one for translucent gas, so rather low density and low AV regions, and one for dense gas. So this corresponds to the usual empirical distinction, but it also corresponds quite well to the different peaks we see in the distribution of the AV in our field in our Orion. And one important point here is that in dense gas, in addition to the other parameters, we also explored a depletion factor to account for freeze out of CO on the grains by a factor between 1 and 10. And we chose a list of potential observables that we can detect in our field. So this is for the model grid. Now, how do we estimate the predictive power of each of those observables? The idea is that for each observable, we will fit some regression statistical model and estimate the quality of this fit. We could use, for instance, mean square error, but we will use the R-square parameters, which is completely equivalent, and just measure the fraction of the variance that's explained by one predictor. And what we use as a regression model is random forest. So random forest is a very common now machine learning tool, which is based on the idea of decision trees. So decision trees do regression by simple piecewise constant prediction with splits that are built into a tree with the choice of the split value and split variables, which are optimized to get the best fit of the data. Of course, if we want a tree model that's flexible enough to account for any kind of nonlinear relationship, it will usually have very bad overfitting problems, which is why in random forest, the new concept of bagging is used. The idea is that if you have many different regression models that are all overfitting, but that make errors that are statistically independent, if you average them, then you will get a very good predictor. So here, the independence is built by using bootstrap samples that are given to each different trees so that they don't see exactly the same data, and adding some randomness in the training process. So we applied this to our chemical model grids. So first, for instance, here the results for translucent gas conditions. The first striking point is that we find a lot of tracers that give very good prediction for the ionization fraction. We see here the R-square is higher than 0.9, so more than 90% of the variance is accounted for by just one predictor. So here we used ratios of observable quantities to get rid of some geometrical effects. And you see here, for instance, the kind of relationships that we get on the right side between some of the best tracers that we have found. We see that there is still some scatter around the main relationship, but this is of course due to the fact that we completely ignore the values of all the other unobservable parameters, such as density, temperature, H2 or SO2 power ratio, and so on. In those conditions, translucent gas, of course, ionization fraction is still dominated by photons. For instance, HCN over CN, which is also known to be related to the UV field, as CN is a photodissociation product of dense gas, where the quality of the relationships we found are a bit lower, but still very good. So I think the very important point to remember here is that we are we have 7 physical parameters that are considered unknown and varied in the grid: gas density, H2 SO2 power ratio, depletion. Despite all of those unknowns, we can, from one single observable ratio, get a pretty good estimate of the ionization fraction. I will skip, of course, the results I presented before were for column density ratios, which are not directly observable. So we also built the same using line intensity ratios, where the line intensities have been computed using radix as a post-processing. But I will skip this to move to the last part, which is that random forest models are very flexible, very good, but they are a bit difficult to provide to users because in a random forest there are hundreds of trees, so the number of coefficients is quite huge. So for a more usable result, we also computed simpler analytical fits using simple polynomial formulas, which we can provide as a table of coefficients in the paper. And we also provide a fit of the scatter around the main relationship so that people can estimate also the uncertainty when they use those formulas. And once we have this, we can start estimating the ionization fraction over a wide field. For instance, you can see on the left the estimation we get for the translucent envelope of the cloud using C2H over HCN, where we see ionization fraction of a few 10 to the minus 5 up to 10 to the minus 4, with the highest values being on the illuminated edge of the cloud. And we can also do the same in dense cores, for instance, using CN over N2H+, where we find the ionization fraction of a few 10 to the minus 7. So I will end here. I think the important point here is that this method is very general. It could be applied to any kind of models, maybe more complex models such as PDR models, to find the best predictors of any unobservable physical quantities that we might want to measure, maybe density, depletions. And we see here that it is generally possible to find good predictors despite a large number of physical parameters. So the first applications I show on Orion B are very preliminary. We will continue working on this. And then, of course, the next step will be to apply this to more complex models and other physical parameters we are interested in. Thank you for your attention.
Excellent. Thank you. Do we have questions locally? We have a question by Alvaro. Yeah, hello, Emily. Really great presentation and exciting results. So I have a question for you, because you were showing many abundance ratios and line ratios. So what is the best ratio that you found that for this purpose, for the ionization? And what I mean by best is not only which one is sensitive, but which one, for instance, is more linear with the ionization, so that you can basically translate one to the other.
Yeah, so, well, I think, so of course it depends which kind of conditions. We split it between translucent gas and dense gas. So I think indeed, it's not only the best in terms of the most sensitive. I think linearity might not be too much of an issue because it's quite easy to build, for instance, a polynomial fit that's a pretty good match to the data. Of course, the other issue is that those lines need to be detectable. So for translucent gas, the best line ratio that we found was C2H over HCN, which has the advantage that both of those lines in our dataset are detected over quite a wide spatial field. While in the dense gas conditions, CN over N2H plus seems to be a good tracer. Of course, N2H plus is detected only on the cold cores, but it's still more pixels than DCO plus.
Very good, thank you. Okay, yeah, thank you. I think we will have to move on to the next talk. We can always continue the discussion online on the YouTube chat. So thanks again, Emeric, for a very nice talk.
Thank you.
Very good. So our next speaker is Cornelia Parks, and I'm really looking forward to some nice Sophia science that she's going to present. I'll just add her to the stream here. This is already all set up. So Cornelia, yeah, please take it away.
Yep. So yeah, thank you. So what I'm going to present is some velocity resolved C+ observations from Sophia take by upgrade towards towards the Orion area. So basically M42 with M43 and NGC 1977 to the north. So I first show you an overview of the whole region. This is basically the left panel is, can you hear me? Okay. So the left panel is virtual photometry. So the two PAX bands at 70 and 160 micron, and the Spire band that's in red, 250 micron. And you can see that the longer wavelengths tend to trace the more filamentary structure, so the integral shaped filament, while the other two basically show a circular structure here and here. And this is what you also can see in the other two images, which is the Sophia data in the middle, so C+, and the 8 micron image from Spitzer to the right. And these two actually show a very good correlation. So why do we use the C+ line? So the C+ line is one of the brightest far-infrared cooling lines of the ISM, and it's a dominant cooling line of intermediate density gas and warm intermediate density gas. So some temperatures around 200 Kelvin, or in densities from 10 to the third to 10 to the fourth particles per cubic centimeter. And the origin of the C+ emission can be dense PDRs, or cold H1 gas, ionized gas, or CO dark gas. And by velocity resolved mapping, we can also try to establish a 3D picture of the whole region. So this again is a C+ image, and so the line integrated intensity. And I marked here some structures that we investigate in detail. So you can see a circular structure here. That's what we call the Orion veil. I will show you in a minute why. And then here in the north is the structure, a circular structure connected to NGC 1977. And here you can see M43, just to the north of the OBC1 core that's here. And I also, I don't know, it's very small. The two stars are theta1 OREC and theta2 OREA. And the other central stars I marked here for M43 and NGC 1977. So we made position velocity diagrams along these cuts here, and I will show you them. In the next minutes. So this is what we first saw for the that's here right through the middle of the Orion veil M42. And what you can see here nicely is that there's an arc structure, which is an indication of expansion of the gas moving towards us, because we can only see it in one direction. And in the lower panel, there's the same structure, but I overplotted the arc structure that's for a background velocity of 8 kilometers per second and expansion velocity of 13 kilometers per second. And this expansion velocity you can also see in the single spectra, where you can see two peaks and one is moving outwards if you go along the PV diagram and moving backward again. So, and from the peak difference, we also estimated an expansion velocity of 10 to 15 kilometers per second. The next structure we looked at was M43. We can also see signs of expansion, but it's not. Yeah, it's more a disrupted arc this time, but yeah, it still looks very nice. So, and from spectra, we estimated an expansion velocity of 6 kilometers per second, which spectra you can see here. And then the next structure was towards the north with NGC 1977. And this time the structure seems to expand in two directions, so away from us and towards the observer, which you can see. And it's very faint, so, and not very clear, but we think that we see significant evidence of that. And it's consistent with an expansion velocity of 2 kilometers per second, which you can see better in this spectrum taken towards the center of NGC 1977, where you can clearly see two velocity peaks and maybe a background of that comes from ionized gas towards the center. So we think that these expanding shells are basically neutral warm gas because the line widths are rather small. And so we also try to think of what's actually the cause of these bubble and the expansions. And what we think is that the large scale expansion of the Orion Nebula, so the veil, is basically driven by the stellar wind, and while the other two are thermally expanding H2 regions. So we compared the wind luminosities, first we tried to establish the kinetic energy that's in these bubbles. So we estimated the mass with various measures, so from the dust or from the density of the shell that we estimated. And for the Orion veil, we got a mass of 2,600 solar masses. And if you then compare the mass to the expansion time and compare these to analytic models, so the Weaver solution for M42 and for the H2 regions we use the Spitzer solution, you get expansion times that you can compare to the integrated to the kinetic energy. And in case of the M42 veil, we basically thought that the wind could be powerful enough to drive the expansion, while in the other two cases, it's clearly not the case. So, summary, so the first large-scale velocity-resolved C+ map of the Orion Nebula. First, we reveals the large-scale expansion of the veil, and other parsec bubbles can be observed towards M43 and NGC 1977. And while the first one, M42, is, we think, driven by the stellar wind, or at least for the most part, the other two are clearly H2 regions expanding thermally. Thank you.
Excellent. Yeah, thanks for a very nice talk. Do we have any questions locally? João?
So the mass, the 2,600 solar mass. Oh, the 2,600 solar masses is really awkward because it's just right there. How it sounds a bit too large. I thought that was the mass of the entire integral shaped filament. What do you mean by
so that's
neutral mass?
That's only the mass of the expanding shell, we think. might be an overestimation because we estimated from the dust map, but it's just the, and it's actually in the order of magnitude of the OMC1 as well. Yeah.
So it's the mass of the entire dust mass inside the nebula.
Of the expanding shell. Yeah.
Thanks.
Okay, do we have Stefan?
Another question. Could you? Yes, I have to move over here. Could you go to the plot where you show NTC 1977? Yeah, this one. I was just wondering, the two peaks that you see here, they have different amplitudes, right? Is there any deeper meaning behind this? So where you have a different height in the peaks for the neck and the foreground?
Well, there might have all kinds of reasons why they're different, right? It could be slightly different temperatures or different column densities. Sorry. But I didn't investigate the details, so I don't know, basically.
Okay. Yeah, we have one more question here. Tom Guess. Another local question here in Leiden.
So this is really fascinating data. One of the questions, I mean, these bubbles are expanding to a very inhomogeneous medium, and your models look very sort of symmetric, at least the way you plotted them. Do you see like the impact of this asymmetric media on the expansion?
That's actually the very weird. It looks pretty symmetrical and spherical and everything. Also, the center stars are clearly offset from the center, and there's all kind of anisotropy and density gradients and whatever. So, but still, the expansion looks pretty spherical.
Okay, excellent. Any more questions? Did anything come in online? I don't see anything. Okay, let's thank Cornelia again for a very nice talk. Excellent. Yeah, so we will move on to our next speaker, Sumaya Suri. While I switch over here.
Hi.
Sumaya.
Hi.
If you could share your screen, then we can
Okay,
actually put it into the stream here.
Share screen.
Sumaya is also an
Okay.
Orion Unplugged alumna. She's also participating in Vienna already.
Okay, can you
excellent.
see my screen?
Yes,
Okay.
yeah.
I'll make it full screen. Okay, I guess you can also hear me.
Now we see a black screen, actually. Did you share the entire screen? So like we see it like this, but not in the full screen view.
Let me try full screen. No, that's wrong.
Did you share the full screen in StreamYard?
Oh,
or did you
maybe-
just share the window?
I just shared the application, so let me try again.
Yeah,
Your entire
then you need to
screen.
share the entire
Okay.
screen. So.
Now
Okay,
the
I see
application
something
isn't
coming
there.
in.
Is that working now?
So if you now go to full screen, perfect. Yeah, excellent.
Is it working? Okay, all right.
Perfect. Thanks
So-
a lot. Yeah, so please take it away.
All right. Hi, everyone. My name is Sumaya Suri. I'm a postdoc currently at the Max Planck Institute for Astronomy in Heidelberg, Germany. And today I'll be talking about the filamentary structure of Orion A. So by now we all know that the filaments are a part of molecular cloud structure, and they contribute to the cycle of star formation immensely by fragmenting or channeling mass to the star forming cores. And why do we care about filaments? One of the biggest reasons that we started caring about them is that over the past decade, Herschel has reminded us that all the filaments, all the molecular clouds in the ISM are pervaded by filamentary structure. And we do not only see filamentary structure in the Herschel column density maps, but we also observe them in a variety of molecular gas tracers, such as this beautiful N2H plus map that Alvaro has created towards the northern portion of Orion A, that is seen in very high resolution, his famous fibers. We also figured out that most of the star formation happens along and at the junctions of filamentary structures, so that's why we basically care about them and we try to understand their properties. So in this particular talk, I will be focusing on two important questions in the context of the Orion A molecular cloud. The first one is, what are the properties of the filaments in Orion A and do they vary? And the latter is, do filaments look the same when observed in different tracers? This first question is motivated by the fact that this particular plot exists. So in their 2011 study, Doris Arzumanian and collaborators, they found that the filament width as a physical property could be universal, and it's equal to 0.1 parsec for most of their filaments. And they speculated that this could be related to a possible formation scenario of filaments via colliding flows within molecular clouds. And the second question is motivated by the fact that many of the higher resolution observations showed much more narrower filaments. So we want to look at different tracers to see if there's any differences. Luckily for me, most of this data is already presented in the earlier session. So I used, I've been a part of the Carmen or Orion survey. So for this work, I used 13CO and C18O emission maps. So these maps were obtained by combining the interferometric data from CARMA and the single-dish data from the Nobeyama 45-meter telescope. I've also been a part of the C+ score degree project that Cornelia has just presented. So I made use of the C+ emission map that was observed with Sophia. I've also used the dust column density map from Stutz and Kahnelein in 2016. In order to work on the filaments, I first needed to identify the filaments. And for this, I know some of you really hate disperse, but I use disperse. So this little movie, I hope you can see it, shows zoom into the OMC1 region. The third dimension here is the velocity coming up again, overlaid with the identified filaments. So we identify about a few hundred filaments, both in the northern and southern part of the Orion A. And once I had the filaments, I developed a method that then evolved into a Python package called filchap that is basically a filament characterization algorithm. So it needs two inputs. The first is obviously your data, and FITS files, it can be 2 or 3D. The latter is the skeletons of your filament. So these are basically the coordinates of each point along the filaments. And it outputs a variety of properties and statistics about your filaments. So filchap is publicly available on GitHub, shameless self-promotion. It was also used in a variety of other works. So one of the most striking things that filchap put out from our C18O data of our filaments was that the filament width changes even along a single filament. So this plot shows the filament width along a single filament calculated using different methods. So basically what you can see is that filament width goes up along the filament and then it goes down again. And then you can ask what happens along the entire cloud if it changes along a single filament. So this plot basically shows the filament overlaid, all the filaments overlaid on the map. And each point along the filaments are colored by the width that is calculated at that particular point. So what you can see is that there's a variation of width of about an order of magnitude. And we attributed these variations to a variety of reasons. So one of them being as the filaments approach the hubs, the widths get larger because things get more tangled. And we also saw that as the filaments inhibit more substructures, their widths get larger. Coming to the latter question, do filaments look the same when observed in different tracers? So I will answer this in 2 steps, one of them looking at the dense gas. So we did the same analysis on the 13CO and the column density map, and we found that the strongest correlation between C18O widths and the and the widths calculated from the other maps exist in 13CO. So, and this is done by looking at the Pearson correlation coefficient. So 13CO and C18O showed strong correlation, whereas the column density, the widths calculated from the column density map and C18O showed weak correlation. And the reason for this is that column density map and the C18O map do not always trace the same kind of structures. So the column density map might be tracing several structures along the line of sight, whereas in C18O we're able to disentangle this, all these structures. And also in the densest parts of the cloud, the C18O freezes out, obviously, leading to larger widths than that calculated from the column density map. The last part, I will be talking about the correlation with the ionized gas. Before I go into that, I will remind you of this beautiful map that Cornelia has already shown. We see several bubbles, and I will be focusing on the interaction between the ionized gas and the molecular gas. So this is C18O map again. What I'm doing here is that I'm looking at radial profiles of different tracers perpendicular to this filament spine. So 0 point represents the spine. At 0, we have all our molecular gas, so column density, 13CO and C18O. And we have C plus shifted from the center along with the shift in the dust temperature in the bottom panel. So what is happening is that this filament is facing a source of feedback, and then the ionized gas and the dust temperature increases. And for those of you who know Orion really well, you might be thinking now, this is happening, this chemical layering is obviously happening in this particular region because this is the Orion bar. It's the most well-known PDR in the entire universe. But if you look at the other filaments, they look more or less the same. So whenever a filament is facing a source of feedback, the C plus increases along with an increase in the dust temperature. So we have also interesting cases such as this particular filament at the edge of the NGC 1977 bubble, where our molecular gas is embedded within an ionized envelope. So we went ahead and characterized this particular layering just by calculating the physical distances between the ionized gas peak and the C18O peak. And then we now color the filaments by this distance. And what this plot is basically showing you is that outside of the very dense ridge of the integral shaped filament, all the filaments show chemical layering between the ionized and molecular gas of about 0.1 parsec. So this is valid for C18O. It's also valid for 13CO. So my takeaway point is that if this is happening, this chemical layering that resembles PDRs, the Orion bar may not be the only PDR in Orion. So I will leave my conclusions here, just basically summarizing what I've just said. Thank you very much.
Yeah, thanks for a very nice talk.
Oh no.
Do we have any questions online or offline? We have one by Alvaro here in Leiden.
Yeah, really nice results. I have a question about your PDR filaments. Do you find any correlation between those filaments with more PDR signatures and, for instance, the width of these objects, or something that suggests compression in these particular regions higher than others due to the external feedback, for instance?
I have not looked at this, but it's an excellent point, actually, that there might be there might be a correlation. I mean, not only the physical width, but also one thing I was looking at is the velocity widths of them. Because if they're compressed somehow, they might inhibit more turbulence than the other filaments. Yeah.
Do we have more questions? Did something come in online? Not yet. Cool. Yeah, thanks again for a very nice talk.
Thanks very much.
Thanks for joining us.
Yeah, thank you.
And of course, we should all remember that we can continue the discussion online in the chat window in the YouTube page. Okay. Our next speaker is Amy Stutz here in Leiden, and I will add her to the stream now. We're already all set with the full screen view. So yeah, Amy, please take it out.
Well, thank you guys so much for organizing this. And I think you guys are doing a great job, by the way, especially with this somewhat complex online system and getting people from all over the world to talk. But anyway, I'm going to talk about the integral shape filament, which we've heard about in some detail now, which is where the ONC or M42 is forming out of. And so on the left, I'm showing our column density map, which we've seen in a few talks. And on the right, I'm showing the Kong 13CO PV position velocity diagram that somebody had just introduced. And I'm going to make one small modification to this figure. So why am I flipping this figure? Why am I just showing it backwards? Because Gaia. So what do we find from the Gaia bind parallaxes? We find these wiggles throughout Orion A. So on the top, we can see the integral shape filament. On the bottom, the more quiescent L1642 region. These results have also been reproduced subsequently. So it looks like the filament has a significant structure in the line of sight. We're going to focus on the ISF. And so what we find is that the gas velocities are correlated with the position into the line of sight of the filament. And it has this wave-like appearance, these wiggles. So we have to emphasize here that these are completely independent data sets, obviously. We're talking about Gaia and ground-based gas velocities. So we're talking about heterodyne versus astrometric, space-based versus ground-based, et cetera. And the comparison between these two data sets, so the black shade and the green shade are the gas velocities, and the red points with both the blue and red error bars are the bind Gaia proper motion, parallaxes, excuse me, yield a timescale of about 4 million years. So if this were the result of something like an initial perturbation propagating through the system, we would expect this to increase like a Hubble flow. So the velocities would increase with position. But because we have a negative sign, there must be a restoring force in the system. So that's why we think we're looking at a wave here. So what could be possible explanations for this type of behavior? Well, we can look at the available forces in nature and immediately scratch off the things on the bottom, strong and weak force. We like gravity quite a bit, right? I mean, everybody here, I think, would agree that gravity is all right. But, you know, it's an inverse square law. So it's not going to provide a restoring force. So we think that we have to look towards magnetic fields, the combination of gravity and magnetic fields, to explain how we can get this wave-like oscillation in the system. And so,
where is the evidence for why is it not just going to the
so the larger the displacement, the larger the velocity pushing it back. So it's going in and out.
Where's the evidence?
The bottom axis is the velocities. So as the displacement from the center increases, so the top axis is the position from the bind parallaxes, right? And so we're comparing the gas radial velocity, so everything's along the line of sight, okay? And so as the displacement from the center is increasing, the velocity is also increasing, pushing it back in. Come back to that at the end. I can show you the math, where this relation for a standing wave comes from. Anyway, previously we predicted that we thought that this filament was oscillating So the basic idea is that the ISF is trapped in an autodestructive cycle of oscillations. And our main evidence for this was the elevated velocities of the YSOs. So we have protostars with about 500,000 years, and then an instant later, they have elevated velocities relative to where the protostars are forming at the bottom of the gravitational potential. So what was our basis for this? Well, the wave shape of the ISF, its mass distribution, severe velocity gradients that we can see here, and the strengths of the magnetic fields, measured from Zeeman in this case, so actual magnetic field strengths, not inferred strengths from polarization. The new thing was that we related the protostar positions, which again are at the bottom of the gravitational potential of the filament, and the star positions, which are more spread out in space, they're separated from the filament, and the velocities of both populations of the protostars and the stars. We put that in the context, in the framework of the gravitational potential of the filament, which we derived from the Herschel mass maps, essentially by averaging over the entire ISF and extracting a mass per unit length profile. So the expressions for the gravitational potential are given at the bottom. And then we also see that in the northern portion of the Orion A cloud, there appears to be periodic cluster formation with a delta T of about 2 million years. We see then a little bit below that, so that's NGC 1981 and 77. A little bit below that, we see the embedded cluster, OMC M42, forming today. And then a little bit below that, we see the quiescent L1641 cloud, quiescent in quotes. Quiescent in the sense that it's not actively forming what we would call a significant cluster. So this thing is repeatedly happening, then quiescent. That was the basic scenario that we put forward. And then we found, from binning the Gaia parallaxes, this behavior that to first order appears consistent with a standing wave, where the displacements are correlated with the velocities, but have the opposite sign. So where do we go from here, now that this issue has been confirmed? So we have a larger scale wave, but we also see structures in the COPV diagram that are consistent with smaller scale oscillations, where the amplitude increases towards the ONC. The ONC is at 0 in this diagram. And then the filament is just getting shredded and completely ripped apart just below the ONC, not at the ONC, not at BNKL, not at the location of a massive star. The filament is just shredded and basically doesn't exist, and then continues below. And so we can dissect this diagram and see that in the top we have this curvature that I showed before. So the left here is the positions along the line of sight. We see the ONC center, which appears to be a region of amplification of this signal. And below, where the gas is turning in the Gaia data, we see that the filament disappears. And then the gas continues below that. So from just the PV information, we can't really figure out what's going on from that alone. But we can dissect other tracers. In this case, what I'm showing on the left is N2H plus diagram. So this is a PV diagram of N2H plus, which has been intensity weighted. So every point reflects the actual amount of emission at that point and at that spectrum. And it shows small scale features. The larger scale structure is consistent with this 13CO, but the small scale features seem to indicate some kind of wrapping structures, which may be consistent with torsional waves. Also, the overall perturbation appears to be propagating north to south because the filament is getting ripped apart in the south. And just to make a quick plug to my students' paper, which has been submitted, we also checked the ammonia data. We get very similar features as an N2H plus. So this tells us that we're on the right track, that these features are real. And then there's interesting differences with lower density tracers, which are shown here. So with that, I'll leave you with my summary, and thank you for listening.
Excellent, thank you. Do we have questions? Yeah, so we will again try to capture this locally here, because as you gather, both the speaker and the audience are here in Leiden. So we have a question from Albert, from Joan.
So I'm just wanting to, can you rule out that the entire ISF is just being blasted by something, some event that took place, I don't know, a couple of million years ago, and the whole thing is just going. Why is it obvious that he has to come back? Just because of the shape of the, I think this is where your argument is, because of the PV.
Well, it's going and coming back. So
Right,
at the same point in time, so you have to blast it in a very specific way.
Right, exactly. Okay. No, but what's hard for me to understand is, because I don't know enough of that, how does you get, it's a really interesting idea, but I just have a hard time visualizing.
It's super weird. I agree.
Oh, okay.
I totally agree. But anyway, this is coming out of the Gaia data. And I think the first thing our job is as observers is to take the data at face value. And then bother the theorists as much as possible.
Because Josefo, exactly, I agree with that. Josefo shows something where
she finds wiggles.
Yeah, she also finds
them, but she found them.
No, the wiggles are in the data. I mean, this is clear.
Yeah. What we did is correlated with the gas velocity.
And it's the same, right?
Yeah.
Exactly. So what I think Josefo will argue is that, if you leave that to potential on the galaxy, the whole thing just continues. And of course, we don't know.
Continues.
The entire ISF, the entire head of the cloud, will be, I guess, you'll see a movie later, which just continues behind the tail of the cloud. I mean, the entire cloud there's a large gradient, there's a large tail, and the band head. And what we will argue is that this is just a product of some feedback effect.
What feedback?
Well, supernovae, massive stars, there's plenty in front of Orion. And so maybe this is a great topic for
absolutely
a conference where we go to the bottom of this. One of us cannot be right. And I think this is perfect forum for this discussion. And I thank you for your talk.
Okay, thank you. Yeah, we have another question locally here in Leiden.
Yes, so thank you for your talk. As you said, it's weird. One thing that I didn't quite understand is, because I do think it's a really cool idea, what did you mean by the wrapping behavior? Because I wasn't quite clear on
this is more speculative, but we see in the N2H plus these smaller scale features that look like I'm already being vague, and I'm fine with that. There's structures that are wrapping around, so they may be consistent with a torsional, like a corkscrew type structure.
Right.
The reason that we, I prefer to talk to people.
It's fine.
Anyway, the reason that we think that there's a possibility of a torsional type of wrapping structure is that we think that there could be rotation in the cloud, and also that the magnetic fields could be helical. So the data that we have are consistent with that to first order. We see a flip in the magnetic field direction as you cross the filament. So the filament, you see the magnetic field flipping from Zeeman, and then you see that the Planck, for example, polarization vectors are perpendicular to the filament. We can argue about that interpretation because it's a model, but it is an actual possibility that this thing has helical field, that the material is wrapping and it's just going down to smaller scales. It's speculative.
No, but that's I wondered where the part came from, but that's thank you.
Thank you.
Okay, thank you. Do we have more questions? We have a question by Alvaro.
So, because you immediately rule out gravity, and since we have...
No. I said I like gravity.
You like gravity, okay. But your interpretation is based more on the... Yeah. So particularly now that you are showing this N2H plus map, we publish almost identical data. I don't know which data are this, but N2H plus map of the entire region, and actually has kind of similar plot. And then this big wiggle that you see...
just below the ONT.
Yeah, so this is our interpretation is a gravitational collapse. So I would like to know how these things fit together or not, or we need to discuss this in more...
I think we need to discuss in more detail. So to first order, the mass distribution is fairly constant along the ISF. But of course, that just showed you a big break in the filament. It's not actually constant. So then we calculated the density profile in the same way that we did for the entire ISF. We also calculated it just in the ONC. They're not radically different, but they are different enough to get some effects, on the field. Absolutely. So it cannot be magnetic fields alone. I mean, this thing has mass.
No,
So we can't, I'm not saying gravity's not a thing.
No, because we could explain, again, we can disagree on it, but we explain this
the
wiggle.
overall morphology of the thing doesn't look like gravity alone.
Well, we can discuss it because, again, this profile we could explain with pure mass distribution because there you have a lot of stars. You have 2,000 mass, solar masses in stars. That is not obviously in N2 Plus or any other tracer. But perhaps we can discuss this. This would be a good point to discuss.
So we also compared the gravitational field in the EONC of the stars, estimated from Tom's Spitzer map, to the gas. And we found that the system is gas dominated everywhere, and that's the region where we have the most stars. But I agree, the stars.
I think we disagree in this part. We can talk later. There are more questions. I think it's important also to continue.
Okay, yeah, we have another local question.
I think returning to Zhao's point, if it's a wave, then in some frame, momentum has to be conserved. So the momentum in the part of the wave that's moving to the right on your picture, there has to be some momentum going to the left in some frame of reference that will drag it back eventually.
Well, I don't have a good answer to that question. Well, what's the question?
Okay.
Is that it? I'm not sure. I think it's a standing wave, right? So we're going to have waves propagating in two directions, adding together. That's what it looks like to first order.
Okay.
Well, it comes right out of the math. So if we just sum two waves, we get this relation. So it's got to be more complex than that. And it's not a perfect correlation. But that's the behavior, the classical behavior of a standing wave.
You don't need traits.
There should be some line of sight projections and other complexities. And probably we do need more constraints, but I think it's a good first order approximation.
Okay, are there any more? Okay, so are there more comments or questions? Was there anything online lately? Okay. Okay, so let's thank Amy again. And we are now actually, for our last talk, we'll move back to Heidelberg, to Juan Diego Soler. And I will put him into the screen here.
Great.
So if you could change to full screen, perfect, excellent.
Okay.
Okay, so please take it away.
First of all, many thanks for giving me this opportunity to speak today. I'm really, really sorry. I'm actually sad that I cannot join you in Leiden in this moment, but I had a very good excuse. So I'm going to talk about magnetic fields in and around Orion. So let me begin with the summary of my talk. This is a summary of my talk. This is most of what we know about the magnetic field towards Orion and its neighborhood. So Orion is in a larger vicinity that we call the Orion-Eridanus superbubble. And we know about the magnetic field through three kinds of observations. So these observations are mostly sampling the neutral medium in Orion. The first observation is the Zeeman splitting. The next observation is dust polarized emission and absorption of starlight. And I'm going to talk about two little results that we have on that, on using that data. And the third result that I'm going to talk about today is using Faraday rotation. So if you remember the textbook definition of Faraday rotation is mostly sensitive to where the free electrons are. But it turns out that using a very small trick developed by Merouche Tahani, a student at the University of Calgary, now we can sample the neutral medium using Faraday rotation. So let's not stand in ceremony, let's start. So this is the view of Orion that was provided by the Zeeman split H1. A very dense medium, but the observations of OH are only a pair of them and they're non-detection. So this is the picture that we get. So we have the magnetic field coming out of the screen if you see a box, and coming into the screen if you see a little cross. So these were obtained by Carl Heiles, and most of these magnetic fields are consistent with 10 microgauss or less. That's where we got that impression of the wrapped magnetic field around Orion that Amy was describing before. So Same observations are really hard to get. Careers go on that, but if actually we have more observations that expand towards these larger structures. So there you can see in red the molecular clouds. In the right you see Taurus, and in the left you see Orion with all of the Seyman observations around. And then you see that long rim in H1, that is the Orion Eridanus superbubble. So if you want to extend what we learned from Seyman, there have been not so many Seyman observations made since the time of Carl Heiles. You have to go to polarization. So you guys know this plot, so I don't need to stop so much. So the starlight polarization reveals the magnetic field between us and the stars, whose light is unpolarized, and it was basically a mess. So this is the picture in 1997 when Carl was first reporting his Orion data. But now we have a different picture. And Orion is very particular, is very interesting for polarization, because actually the first ever polarization vector measured in emission in the far infrared was measured with a balloon, and it was towards M42. And then the second two polarization vectors were measured actually in 1984 using the KIO at 270 microns. So the first observation of those polarization, well, they were made towards Orion. Now the picture has changed a lot, and this is the current picture of those polarization that we obtained thanks to Planck. Planck observed the whole sky at 353 gigahertz. We assume that this polarization is representing well the magnetic field, so we just rotate it by 90 degrees and produce these maps that are made using the line integral convolution algorithm. So what you see here is this drapery pattern corresponds to the magnetic field. The colors here, the blue corresponds to H1, the red corresponds to CO, also from Planck, and there you can see the Orion stars just for reference. You can see Orion A and Orion B very clearly, and this links Orion to this larger vicinity. Orion is at the edge of a very large bubble that was produced by multiple generations of supernova explosions with energies that amount to 10 to the 54 ergs. And these several generations of stars have created this bubble that is at around 200 parsecs from us. You heard the talk by Sarah Rezaei yesterday. The distance is not well established, but we know that this is a very nearby object that is touching on the one side Taurus and on the other side Orion. However, determining the exact geometry of Orion Eridanus is very tricky, but we know this is the vicinity that we're dealing with. So this is a very interesting neighborhood. So if we zoom in 2016, I published this data with Planck, because what do you do with this kind of maps? You cannot get the magnetic field directly, the magnetic field strength. So unless you use Davis Chandrasekhar Fermi, that I don't like so much, you can get a number, but the Planck beam enhances the kind of the magnetic field strength that you get is very high. We circumvent those assumptions by just comparing two things that are evident to your eyes right now. And it's what is the relative orientation between the magnetic field that you see in the drapery pattern and the column density structures that you find there. So what I found is that the magnetic field changes from mostly parallel to mostly perpendicular towards Orion as well. So this is consistent with what we saw in most of the Gould belt clouds, where the relative orientation with this parameter C going from positive to negative, that is telling you that the magnetic field, that's telling you that the magnetic field is oriented mostly parallel at low column densities, mostly perpendicular at high column densities, okay? And you can only see that in MHD simulations where turbulence and magnetic fields are at least in equipartition. So of course, this is 2016, so we took a step forward, and instead of comparing column density and magnetic fields, both from Planck, we compare this time column density and magnetic fields from Herschel. So the magnetic field comes from Planck at 10 arc-minutes resolution, and the column density maps come at 36 arc-seconds resolution from Herschel. So I'm not guessing the magnetic field at smaller scales. I'm just asking the question, what is the relation between the structures that we see with Herschel at higher resolution and the magnetic field that we see at lower resolution with Planck? What is the idea behind that? The magnetic field is going to be there anyway. So if the magnetic field is strong enough, you would expect that the structures in density that you form at lower scales have to keep some memory of the larger scale magnetic field. That is the concept of anchoring that some other authors have been discussing. Well, I wanted to test that quantitatively. So I characterized the density structure using their gradients. And what I found is that for the three subclouds of Orion, that this time I can sample with Herschel, I find that this trend is the same. So the relative orientation goes from mostly parallel at lower column density to mostly perpendicular at higher column densities. So I smartened up a bit during the last 3 years. So I'm not using only the relative orientation parameter, that is the first panel, that is the same one that I use in Planck. I'm also using circular statistics. So this V, that is the projected Rayleigh statistic, that is a likelihood test that the distribution is centered around a certain angle. Basically, that is a smart talk for, I just know circular statistics now. And also we plot the angle in the lower panel. What you see is goes from mostly 0 up to close to 90 degrees, can be like 70, but the uncertainty is very large, okay? So we're seeing that also the structures that we see in density with Herschel go from mostly parallel to mostly perpendicular with respect to the magnetic field. That is very cool, and actually you can see it by eye. This is just a quantification of an impression that you get. So if you look at this map, you see that the densest part of this map are perpendicular to the magnetic field that is sampled here by Planck, okay? So it happens both in the right, where you have most of the star formation in Orion, and towards the left, where you have kind of this fish tail that is also perpendicular in the highest density parts. So just a trivia question, when you look at this map enough, then you go to a museum to relax, and then you see that this paint by Haim Soutine also looks a lot like Orion, but that's just me going crazy. So before you actually start seeing paintings that look like Orion, we wanted to see if we can get further estimations of the line of sight magnetic field. So, of course, to complement what we could get with the H1 in Seyman. So in collaboration with Merouche Tahani, who developed this method, we tried to use the Faraday rotation observations to generate estimates of the magnetic field along the line of sight in molecular clouds. So how does this go? It turns out that in synchrotron polarization observations that you use to observe those point sources, so all of those point sources on the map on the left, they correspond to distant quasars. You can use those to infer what is the magnetic field that is related to the cloud. And you use a simple trick, you take on and off positions. You know that the background contribution would be the same for the on and off positions. The only difference would be the contribution of the molecular cloud. So there in the right, you see the on and off position. You know that the difference between the Faraday rotation in the on position, in the on cloud position, and the off position is going to be just the Faraday rotation that is due to the free electrons and the magnetic field in the cloud. So then you have just the free electrons in the cloud as the only parameter in that equation. So what you can do is use a chemical network. So Merouche and René Ploux, they use a simple chemical network to estimate the electron density in the Orion cloud. And using that equation that I show here, they produce this map of line of sight magnetic field. These are line of sight magnetic fields. They estimate magnetic fields of several hundreds of microgauss. So of course the error bars are large because the chemical network has large uncertainties, and we don't have so many point sources, some strong radio sources that we can use for the Faraday rotation. So the bad news is that the uncertainties are large, but the good news is that there are more and more surveys that are going to do this kind of observations. So this is the TSS09 survey that has like one source or a few sources per square degree. There are surveys that have now a few, up to tens of sources per square degree. So we expect to get better estimates for the line of sight magnetic field. So what Merouche wanted to do with the Orion cloud was to see what is the model that best fits for the 3D configuration of the magnetic field around Orion. So you see in the right, you have the drapery pattern from the magnetic field that we infer from Planck. So I went against my principles and calculated some magnetic field from Davis-Chandrasekhar Fermi. It gives you like 100 Gauss, 100 microgauss with a huge uncertainty. And what Merouche saw is that there are strong evidences of the reversal of the magnetic field left and right of the main body of Orion A, but we don't have any evidence against or in favor of the magnetic field being wrapped around the cloud. We don't know if it's around the cloud. For sure, we see the reversals, and this is a second piece of evidence. We're seeing the reversals in H1, and now in the lower right, you see that at the end of the fishtail, there's like a little spot that can be seen as a bubble. Well, it turns out that that is the subject of the last of the results that I'm going to show you today. This is Kappa Orionis, and Kappa Orionis has this kind of loop that was always suspicious. We always thought that we saw many loops in the Planck data, and most of them were empty, or is just the drapery pattern that is giving you the impression of a bubble. Well, that was not the case. With this one, was the only candidate that we had a source in the middle. And what made us think about it was not only there's a star in the middle, and it's a very famous star, it has the name, this is Kappa Orionis, but also the proper motion of this star is in the direction of the elongation of this bubble. So we tried to understand what is going on there. So we have another piece of evidence, and it's the fact that if you see the 12 and 25 micron, well, more the 12 micron emission towards Orion A, you also see that there's some shade in that emission. Or Kappa Orionis is a B star with a strong wind, so it doesn't produce enough ionizing photons to be bright in H alpha around it, but the winds can be powerful enough to produce heating of the surrounding medium. So we think that this can be the effect of Kappa Orionis. And the second piece of evidence is if you take a simple model of how the polarization of a magnetized shell would look like in the usual polarization observables, intensity, polarization fraction. My student Henrik Roux, that is leading this analysis, was using also the vorticity of the magnetic field in the plane of the sky and the gradient of polarization. It turns out that these quantities that you see there, that's how a magnetized shell should look like. We have a little problem, and actually Sarah mentioned it yesterday, and Joao was very accurate with his question, and is we don't know where are these structures. So with Sarah, we're trying to decompose in 3D the density structure that can be producing this, because we actually don't know if Kappa Orionis is at the same distance as the dust that we're seeing. So the current observations of the distance to Kappa Orionis are 220 parsecs. Most of this material would be at 400 parsecs. So one of us is wrong. Either this shell has nothing to do with the star, or the star is further away. But we're still investigating that. So this is open. It's not conclusive yet. We just have to wait and see. So of course, this was just a small cut of what you can learn from the magnetic field in Orion. So in the larger scales, you have Orion Eridanus superbubble. In the middle, you have the molecular cloud complex. So you see the Orion A, Orion B. In the past year, there has been amazing observations of the OMC1, this region where there's lots of star formation that have come with Sophia and Pole 2, but unfortunately, I don't have any more time to talk about those today. So I'll just leave you with my conclusions, and thank you very much again.
Excellent. Thank you. Thanks for a very nice talk. For the questions, I will start with a question that came in online by Marina Kunkel. If there are any doubts regarding the parallax of Kappa Orionis of 200 parsec versus 450, how can we trust its proper motions?
That is an excellent question, and Marina is an expert on this. So I know that this distance of 220 parsecs come from the fitting of the proper motion versus distance to older stars. So they use the calcium-2 proper motions for older stars and their parallaxes. But for example, in this case, this star is too bright for Gaia parallax. So we don't have a good distance estimate for that. So we're trying to generate better kinematic, luminosity distances for Kappa Orionis. And the parallaxes, they come from Hipparcos, so they come from different sources. So to answer the question is, the distance comes from this CA2 fit that I think is independent from the parallaxes, at least in this case.
Okay, thank you. There was okay. There's no question locally. There's another question online by Joao that I will read out to you. So Joao says, one thing I learned from your pipe paper, I will actually put the question right here so you can see it too, is that all Planck polarization is local. Could the difference in morphology between Orion A and B be due to a closer rim of the bubble?
That is actually very possible. So it's a good point that Joao is raising. So part of my cooperation with Sarah is understanding that 3D structure. So Orion B is much higher, so it can be seeing a larger background. So that can be possible. Although these are pretty high galactic latitude clouds, so there's not so much dust behind them. But it is a possibility. So we're trying to disentangle that in two ways. First, we're trying to look at the dust versus distance using the methods of Sarah, and the second way is now we have Gaia, and we have the starlight polarization. But it turns out that there are not so many stars in the vicinity of Orion. So we're missing stars. So you'll be hearing more from us when we have more stars with the starlight polarization and distances from Gaia.
Okay, excellent. Are there any more questions or comments? Okay, if that's not the case, let's thank Juan Diego again. Very nice talk. And yeah, that concludes our session. We'll be back in a couple of hours and see you then. Thanks for listening.